This is video 1 for the electrostatics unit. So for this unit, we have these four big ideas. First big idea, objects and systems have properties such as mass and charge. The systems may have internal structure. Idea 2, fields existing in space can be used to explain interactions. Idea 3, the interaction of an object with other objects can be described by forces. And object 5, changes that occur as a result of the interactions are constrained by conservation laws. So these are all big ideas we've seen before. We're just going to apply them to things that have electric charge. So the learning goals. I want you to be able to challenge the claim that an electric charge smaller than an elementary charge has been isolated. I want you to be able to make claims and predictions about natural phenomena based on conservation of charge. I want you to be able to use Coulomb's law to make qualitative and quantitative predictions about interactions between two-point charges. I want you to be able to make quantitative and qualitative predictions about the potential energy for a system of charges. And I want you to be able to make qualitative and quantitative predictions about the electric field for a system of charges. So to get us started, let's talk about electric charge. We've probably all experienced some form of static charge or static shock, usually on a winter day. So this happens when we have an excess of electric charge accumulating on our bodies. That electric charge then finds its way back to the ground, usually in the form of a tiny little spark off of the end of your finger. To understand how the electric charge gets onto us, though, we need to understand what an atom is and what valence electrons are. So when we have two objects rubbing past each other, valence electrons will be pulled off of one object and deposited on the second. So this gives the object that loses electrons an overall positive charge, and the other atom that gains the electrons a negative charge. Now, for some knowledge here, there are only two kinds of electric charge. A neutral object or a neutral system will contain equal amounts of positive and negative charges. The exception, some fundamental charges or some fundamental particles will have no electric charge. Like charged objects and systems will repel, so positive repels positive, negative repels negative. Unlike charged objects or systems will attract, so positive attracts to negative. Charged objects or systems may attract neutral systems by changing the distribution of charge on the neutral system. We'll talk about letter B pretty soon. The smallest observed unit of charge that we can isolate is the electron charge. This is also known as the elementary charge. It has a value of 1.6 times 10 to the negative 19th coulombs. That is the smallest charge we have been able to isolate. Electrons have a negative elementary charge, so electrons are negative 1.6 times 10 to the negative 19th, whereas protons have positive 1.6 times 10 to the negative 19th. So they have equal charges, just different, one's positive, one's negative. The mass of the proton, however, is much, much, much larger than the mass of the electron. So this brings us to other kinds of materials that we can classify. So we have insulators and conductors. So materials that restrict the flow of charges are called insulators. So some materials that are examples of insulators then would obviously be like rubber, glass, and air. Air is an excellent insulator. Conductors then are materials that will allow the flow of charges. So examples of this, most metals. Carbon, if the carbon atoms are arranged in the right format, in water, but the water must have dissolved ions in it. Pure water, believe it or not, acts more like an insulator. Now we have different ways of charging objects. So the first one is charging by contact. So I kind of mentioned this before. When two insulators are rubbed together, the electrons, or the valence electrons, are ripped off of one insulator and placed on the second. And the object which loses electrons becomes positively charged. The object that gains will become positively charged. I'm sorry, negatively charged. The two oppositely charged objects will then be attracted to each other. So if I have, let's say, object A and object B here, and object A gains electrons, it's going to become negatively charged. Object B is losing its electrons, so it becomes positively charged. Since these are now oppositely charged, there will exist internal forces within this system, so electric forces, if you will, that are equal in strength, opposite in direction. So I put a little mark here beside the force on the right here, just to show that it's an interaction pair. So there's our two forces. This is our system. The nomenclature we use, we typically use a Q for charge, so this would be like the charge on particle A, so maybe I'll say it's -3 coulombs, and then I can say the charge on B would equal +3 coulombs. Also, because of conservation of charge, the amount of charge that I remove from object B, so if I remove 3 coulombs worth of electrons from object B, it will get a charge of +3 coulombs, and object A will get a -3 coulombs. But this is kind of a general idea for how this can work. Typically we use a capital Q for big objects. We use a lowercase q for like small objects or test charges. And we measure the units in terms of coulombs. Now this helps explain why hair will stick to a plastic comb after you run the plastic comb through your hair. So what's happening is, as you run the comb through your hair, electrons are being pulled from one and stuck to the other, and that gets them oppositely charged, so that then the hair will be attracted to the plastic comb. So this is charging by contact, rubbing two things together. Sometimes it's also called charging by friction. The second way is called charging by induction. So this takes advantage of the fact that electrons are free to move around in most metals. So, and keep in mind also that the protons are locked in place, so the protons cannot. So here's what we do. We take an insulator, or I'm sorry, a conductor, a neutral conductor, and we bring a charged object close to it. So right now this charged object has a negative charge, and it's pushing all of the electrons to the other side of this neutral conductor. So this neutral conductor, half of it becomes positive, the other half becomes negative. That then exerts a force between the charged object and the neutral conductor. So the neutral conductor will be attracted or pulled towards the charged object. And notice that the same thing would happen if the charged object were positive. If it were positive, it would pull all the electrons to the other side and the signs would just flip, but we would still see an attractive force between the two. So we are inducing a charge on that neutral conductor. We are pushing the electrons around. This is how lightning works. Due to particles rubbing against each other in clouds, we get charged by friction or contact inside the clouds. Through various processes, the charges become split. So the bottom half of the cloud becomes negatively charged, and that induces, you see the Earth kind of acts as a neutral conductor. So it's going to induce a positive charge on the ground below. Now we're going to learn later that this is going to create an electric field. And the electric field, when the electric field reaches a certain strength, we get a static discharge or a breakdown of the air, which we call lightning. And notice the lightning can go between clouds, it can go inside the clouds, it can go from cloud to the earth, all of that. But we'll talk more about what an electric field is later. The third way is charging by polarization. So certain molecules, such as water, can be offset. So here's our water atom, or atoms, or molecule I should say. So we've got our two hydrogens and our oxygen. And if we look at this, the side with the hydrogen atoms is typically positive. The side with the oxygen atom is typically negative. So what we can think of it is kind of like this half positive, half negative thing that's free to rotate. So when I bring a charged object, say it's negatively charged, it's going to induce a torque on each water molecule, causing them to rotate. So all of these water molecules initially are kind of random, but then they rotate to match the charged object or to be attracted by it, and then that'll create a force which will pull the water towards it. So by polarizing it, we're basically taking dipole charges and then we are flipping them around. All right, that's going to conclude video 1.